Hey, welcome back to Combinatorics. In today's video, we're going to focus on counting, probability, lotteries, combinations, and permutations. We'll use the combinations in examples of real-world lotteries, and we'll learn about combinations and permutations in general. In the first part of this video, we're going to focus on counting, basic probability, and lotteries. A specific lottery in particular. And before we get to that lottery, let's quickly review a few reasons why we want to learn combinatorics. One reason is to make algorithms more efficient. Another reason that we talked about before is to optimize costs for processes. For example, a salesman traveling from city to city, choosing a path that minimizes their cost of gas. Another use of combinatorics is in gambling. And today, we're going to focus on the gambling. There's many examples in gambling in which we can use combinatorics. Poker, of course, sports gambling and fantasy sports, and lotteries. And today we'll focus on the lotteries. Some of the most famous lotteries you've probably heard of: Powerball, Mega Millions. And there's also lotteries in sports where teams determine their draft position. And even in colleges, there's lotteries for dorm room choices. So we're going to focus in this video on the NBA draft lottery. In particular, we'll learn about and we'll apply combinations to calculate some probabilities about the NBA draft lottery. Which probabilities will we look at? Well, we'll look at the probability that the Jth worst team by regular season record gets the Kth pick in the NBA draft. So before we calculate any probabilities, let's first discuss how the process works for the NBA draft lottery. So there are 14 ping pong balls. The balls are numbered 1, 2, up to 14. And they're placed in the lottery machine. And then 4 balls are randomly selected, one at a time, from the machine. Note that the order in which the balls are drawn does not matter at all. So for example, if we drew the balls 1, 2, 3, 4 in that order, that's the exact same combination as drawing the balls 2, 3, 1, 4, or 3, 4, 1, 2, or 3, 1, 4, 2, and many other orders. There's one combination that doesn't get used. Any ordering of the numbers 11, 12, 13, 14 is discarded. The remaining combinations, besides that one, are assigned to the 14 teams in the NBA draft lottery. The team whose combination is chosen gets the first pick in the NBA draft. And then we repeat the same process to determine the first 4 picks in the NBA draft. Note, however, that if during that process for the first 4 picks, we choose a combination from a team that was already chosen from an earlier pick, then we will discard the combination. For example, if some team gets the first pick, and then later on that same team has one of their combinations selected for the third pick, the combination that they had selected for the third pick will be discarded because that team already got the first pick. After the first 4 picks in the draft are determined, the remaining teams in the NBA draft lottery are ordered just by the worst regular season record. So here is the first combinatorics question that we're going to look at involving the NBA draft lottery. How many total combinations are assigned to the 14 teams in the NBA draft lottery? So what do we need to count to answer that question? We just need to count how many combinations of 4 numbers are there that we can choose from 1, 2, 3 up to 14, except for the combination that has the numbers 11, 12, 13, 14. In order to count this quantity, we can first look at some related quantities that are a lot larger, and then we can try to modify those to get the quantity that we want. The first related quantity that we'll look at will be sequences of 4 numbers, x1, x2, x3, and x4, that we can choose from 1, 2, 3 up to 14, assuming that we're allowed to repeat the same number any number of times. We have 14 choices for x1 because we can use any number 1, 2, 3 up to 14. We have the same number of choices for x2 because the choice of x1 has no effect on the choice of x2. There are 14 choices for x2, all the numbers 1, 2 up to 14. It's the same thing for x3. There are also 14 choices for x3. And same for x4. Regardless of the choices for x1, x2, and x3, there are 14 choices for x4. In total, there are 14 to the 4th choices for a sequence of 4 numbers that we can choose from 1, 2, 3 up to 14, assuming that we're allowed to repeat the same number any number of times. And 14 to the 4th gives us 38,416. Now, this does not answer the question that we were trying to answer. We want to know how many combinations of 4 numbers are there that we can choose from 1, 2, 3 up to 14, besides the combination 11, 12, 13, 14. In order to count that quantity, we can count another quantity that is more helpful than the one that we just counted. It's another sequence quantity, but now it's the number of sequences of 4 numbers, x1, x2, x3, x4, that we can choose from 1, 2, 3 up to 14, assuming that we're only allowed to use each number at most once. So we cannot repeat any number. We can look at the number of choices for x1 first. Again, like the last problem, we have 14 choices for x1. For x2, we get a different number of choices than for the last problem. Here we have 13 choices for x2 because we can't use the same choice that we made for x1 because we're not allowed to repeat numbers. For x3, we only get 12 choices because we can't use the choices that we made for x1 and x2. Finally, for x4, we only get 11 choices because we can't use the choices that we made for x1, x2, or x3, but we can use any of the 11 other numbers. So in total, we get 14 times 13 times 12 times 11, and that gives us 24,024 sequences of 4 numbers, x1, x2, x3, x4, that we can choose from the numbers 1, 2, 3 up to 14, assuming that we don't repeat any numbers. So there, again, at the top, is the problem that we're trying to solve. And so far, we have not computed anything about combinations yet. Everything that we've computed has been about sequences instead of combinations. And we found that there were 24,024 sequences of 4 numbers that we can choose from the numbers 1, 2, 3 up to 14 if we're not allowed to repeat any numbers. Again, we don't want to count the sequences. We want to count combinations. What is the main difference here? In the combinations, the order does not matter. In the sequences, the order does matter. We can get the number of combinations, though, by dividing the number of sequences by a certain number. So let's consider any combination. We have 4 distinct numbers, A1, A2, A3, and A4, and the order does not matter in the combination. And here's a question. How many sequences x1, x2, x3, x4 are on the numbers A1, A2, A3, A4? We can calculate it the same way as we've been doing. We have 4 choices for x1. It can be any of the numbers A1, A2, A3, or A4. We have 3 choices for x2 because we can't use the choice that we made for x1. We have 2 choices for x3, and we have 1 choice for x4. In total, we find that there are 4 times 3 times 2 times 1, which is 24 sequences x1, x2, x3, x4 that are on the numbers A1, A2, A3, A4. What does this mean? Well, this tells us that there are 24 times as many sequences where we don't have any repeat numbers as there are combinations of 4 numbers that can be chosen from the numbers 1, 2, 3 up to 14. So again at the top, that's the problem that we're trying to solve. How many combinations of 4 numbers that we can choose from 1, 2, 3 up to 14, except for the one combination with the numbers 11, 12, 13, 14. We found that there were 24,024 sequences of 4 numbers, x1, x2, x3, x4, that we can choose from 1, 2, 3 up to 14, assuming that we're not allowed to have any repeats. We also found that there are 24 times as many sequences, x1, x2, x3, x4, with no repeats, as there are combinations of 4 numbers that we can choose from 1, 2, 3 up to 14. So if we want the number of combinations of four numbers that we can choose from 1, 2, 3 up to 14, we can just divide the number in the first bullet by the number in the second bullet. In other words, we get 24,024 divided by 24. And this gives us 1001. Now the quantity that we wanted was one less than that because we're excluding the combination 11, 12, 13, 14. So we get 1001 minus 1, which equals 1000. So we found that there are 1000 combinations of four numbers that we can choose from the numbers 1, 2, 3 up to 14, besides the combination on the numbers 11, 12, 13, 14, which is discarded. So these 1000 combinations are split between the 14 teams in the NBA draft lottery, except the teams with worse regular season records get more combinations. More specifically, the three teams with the worst regular season records are each assigned 140 combinations. The team with the fourth worst regular season record is assigned 125 combinations. The team with the fifth worst regular season record gets 105 combinations. The sixth worst team gets 90 combinations. The seventh worst team gets 75 combinations. The eighth worst team gets 60 combinations. The ninth worst team gets 45 combinations. The 10th worst team, they get 30 combinations. The 11th worst team gets 20 combinations. The 12th worst team gets 15 combinations. The 13th worst team gets 10 combinations. And finally, the 14th worst team only gets 5 combinations. Now let's look at some questions about probability. Before we look at anything with probability though, let's briefly discuss what is probability. Well, if you look in the Merriam-Webster dictionary, here's a definition: the ratio of the number of outcomes in an exhaustive set of equally likely outcomes that produce a given event to the total number of possible outcomes. So we want to calculate a ratio. So here is a question about probability in the NBA draft lottery. What is the probability that one of the 5 worst ranked teams in the regular season gets the top pick in the draft? So first, let's look at the denominator in our probability calculation. For the denominator, the possible outcomes are the 1,000 possible combinations of the numbers 1, 2, 3 up to 14, except for the one that has the numbers 11, 12, 13, 14. Note that all of these combinations are equally likely. And it's fine to ignore the outcome where we choose the numbers 11, 12, 13, 14, since whenever we choose those numbers, we always discard them and redraw until we get different numbers. For the numerator, we just count the number of outcomes in which one of the 5 teams with the 5 worst regular season records gets the top pick. The number of outcomes where one of the 5 worst teams gets the top pick is just the number of combinations belonging to one of the 5 worst teams. That number of combinations is just 140 times 3 plus 125 plus 105. And that gives us 650 for the numerator. So the probability that one of the 5 worst ranked teams gets the top pick in the draft is 650 divided by 1,000, which is 0.65. Now, here's the problem for you. Suppose that the 1st, the 3rd, the 10th, the 11th, the 12th, the 13th, and the 14th worst ranked teams by regular season record are from the Western Conference. And suppose that the 2nd and the 4th and the 5th and the 6th and the 7th and the 8th and the 9th worst ranked teams are from the Eastern Conference. And the problem is to find the probability that a team in the Western Conference gets the top pick. That brings us to the end of part 1 of this video.